Welcome. We are live. My guest tonight is David Chester, the one and only from Quantum Gravity Research Group. He is one of the associate scientists with Quantum Gravity Research Group out in. Or are you still with them, or are you?
You can actually, those are the affiliates. I think if you go to scientists, there's another page. Yeah, that page right there.
There you are. Here he is.
Yeah,
Yes,
so
I've
I used
seen.
to work for them full time. Now I'm still loosely affiliated.
Nice. What are you doing these days mostly?
Well, now I'm looking into alternative propulsion research and trying to look into the depths of electromagnetism and gravity and trying to see if there's novel applications for propulsion. So yeah, I mean, there's been a lot of it really stems from trying to understand what is the quantum vacuum and trying to understand really gets into controversial topics, but are there ways to extract energy and momentum from quantum field theory? That's been a goal that would be nice to have, but it sounds too fantastical. It sounds way too good to be true. And there's been tons of bold claims on the internet for decades on, really going back to Nikola Tesla, thinking about getting free energy from this idea that there's this ether that contains energy. Then the ether was essentially removed from physics, and then quantum field theory came in. We have quantum electrodynamics, and then the notion of the quantum vacuum is kind of a modern version of an ether, but then people don't really want to talk about it. If you're famous enough, you can get away with it. If you're someone like Paul Dirac, you can write a paper on it, and no one's gonna cancel you for that. But it's a little harder to just write papers talking about the ether if you're not at that level.
Right. It's an interesting place to be in physics. What do you think about the Nobel Prize this year?
Yeah, I mean, I've only superficially been following it. I heard there's kind of a lot of contention because it relates to AI. But so there's some people that are saying that, oh, it should have been given to something that's more physics related, or other people are saying, some people are commenting that it's a sign that physics isn't progressing. I completely disagree with that. I think it's fine. I don't really try to pay attention too much to who wins Nobel Prizes because, well, it tends to lead to fanatics and egos sometimes. The types of people that are chasing Nobel Prizes. Uh, I mean, if that's your goal, that's great. But
Right.
I don't
Yes.
think that just following Nobel Prizes is the way to really judge the progress of science. And it always takes a couple decades usually for someone to get the prize anyways. So I mean,
Yeah.
yeah, it's just one prize. You can only acknowledge so many people. So
Right.
everyone's going to get into debates. Oh, what was the best discovery? And it's not a well-defined thing either.
Right.
So
Right.
different people have
And there's
different opinions.
always arguments over it. And then I saw my own a bunch of tweets going around showing that well, any AI could be anything. It's a physicist thinks AI is physics, and a biologist thinks AI is biology. And in fact, all these things can be true, but an AI is just another tool, I guess. Um, you know, so
I mean, there definitely is the physics connections. There definitely is the biology connections. I mean, essentially, neural networks were inspired by trying to understand how the brain works, and then it turns out that there's these condensed matter systems, such as spin glasses, that end up having properties that are very similar to neural networks. So, what's really remarkable is when you see systems across multiple disciplines that essentially have the same underlying mathematics, and so that can help bridge interdisciplinary studies. And I think that's really fascinating because, especially now, everything gets so segregated. There's all these fields and subtopics within each subfield. But if you can sometimes study the mathematics and understand how there's different connections, then you can relate widely disparate fields that seem like they should be very different but are actually related. I mean, another example is economics. Essentially, Feynman diagrams, more or less, quantum field theory has been used for modeling economics as well, the stock market. So it's all interesting stuff to me. Oh, I think you're muted, Jeremy.
Yes. So sorry about that. A lot of people said like physics has been falling apart or is lost. A lot of this big argument going on with Sabina Hossenfelder and Eric Weinstein and all those people um, about dark matter, dark energy, all these things. They're it's a bunch of not so easy pieces that aren't quite fitting together and making sense. I guess. And there's also a lot of corruption in science in general. We've seen a lot of the peer review process being exposed. With the Bogdanov affair is one that I pointed out that was my cue that things were kind of going off of a cliff in science. So I think it's awesome that there's PhDs like you out here diving into the fringe and saying, hey, we'll look at crazy stuff. Sometimes we'll even look at. I like to look at nature because nature sometimes nature's had billions of millions of years to figure out a lot of these problems and come up with solutions. And we always find new interesting things when we look into nature. Um, you know the iridophores and how they work to make and chromatophores and how they work to make camouflage in cuttlefish and squids and even they have iridophores which are like iridescent. They can change iridescence, um, and some of the chemical compositions of these things that nature's figured out for changing and adapting to your environment and making things like invisibility cloaks. Um, but as far as warp drives, I don't think any bugs or any animals have warp drives yet. I don't think a cricket or a
Yeah.
grasshopper has evolved that yet. And it's fact. Michael even came to me today, and he made a bet that what if UFOs were intelligent cetaceans like dolphins.
I
But
mean, maybe. I suppose anything's possible.
but how are you gonna know if you don't ask these kind of crazy questions and look? And now we're digging into some of these scientists who are onto some of these strange or fringe anomalies. Like Ken Shoulders. That uh, that recent paper came out. It was a letter from Richard Feynman to Ken Shoulders that
Right.
I had no idea existed. Um, I thought that was interesting. What were your thoughts on that and the
Yeah,
whole?
I mean, it's encouraging to see. Obviously, Ken Shoulders was a respectable researcher, but a lot of people didn't really understand what he was doing, and so at the time, it was kind of easy to just kind of ignore it. And I want to kind of share the opinions of like what it's like to be a scientist, because just because you ignore something, it doesn't mean you're suppressing it. It's just that really at the end of the day, everyone's human. They're trying to work on things that they can understand. So if there's a topic that it sounds like it's out of left field, and it's not that they're just trying to not, they're not necessarily trying to push it down. It's just that if something doesn't resonate with someone and they don't understand it easily, they're less likely to work on it. I think that you have to remember everyone's human. So that's a lot of it as well. That's what's happening. And so Richard Feynman, case in point, he heard this thing, and you always have to make judgment calls, right? You have an understanding of what your worldview is, how you look at things, and you don't have time to hear every scientist out, especially these days. There's so many scientists out there. It's just been exploding. So
Yeah, and
Richard
the
Feynman
internet's
had
just
to make an initial judgment, right? And he thought that the ZVOs were completely baseless, and then he ended up thinking about it more and then apologized because he realized that there was something there. So yeah, kudos to Richard Feynman, just an example of a really respectable scientist. And in terms of corruption, this and that, I mean, I think we're seeing this across the board in society right now. There's kind of this awakening. It's just so much easier to get access to information than it was decades ago or the previous generation. And so now humanity is going through this self-reflection process where we're kind of questioning everything. Politicians, government, military industrial complex, corporations, scientists as well. So I think it's kind of
yeah.
a trend across human culture that's occurring right now. It's really just a product of the times of what we're living through.
It's also wild how there's like rejection of like some science and stuff too. Like, I like to entertain everything, even stuff that's too crazy for people like you, and sometimes so. Like for example, Alex Jones and a couple congresswomen like Marjorie Taylor Greene have been going on about the weather wars. I mean, first they were saying global warming's not real. There's no possible way that humans could be affecting the planet's uh, atmosphere, but now we can control the weather. And I don't know, it's kind of interesting listening to them try to like explain the two and not see the, I was listening
Right.
to Alex Jones like explain about the global warming and how that's a fraud, but they can control the weather. It's without like calling himself out on his own logical inconsistencies. And I seen all the stuff that, we've seen the documents on all this stuff. We know that they can cloud seed. We know that they can create rainstorms. They can prolong like the rainy season. There's a lot of little things that they can do to push the weather. But as far as controlling certain things, Todd came on, and sometimes I need a friend like Todd to pull me out of some of these rabbit holes before I get too deep down, like into all this stuff, because he just pointed out, yeah, they could seed clouds and do regular storms and stuff, but like a hurricane is just, I mean,
that's another level.
It's another level. So then we started hypothesizing on how you actually do that from a physics standpoint. Like if you say the government hired you as a physicist, me and you, and our job is to figure out how to control hurricanes and direct them, right? So I mean, the best I could think of is that you put like you can spray aerosols in certain areas of the cloud, because I mean, really, like if we have satellite-based laser weapons, right? We have satellite-based, nukes, but no matter how much energy you pump into a category 4 hurricane gives off the equivalent of one megaton atomic bomb every 7 seconds. So the scale is orders of magnitude bigger than our most powerful space lasers, our most powerful land-based or naval-based laser weapons. It's orders of magnitude larger than what we could do with just all the electrical grids combined. Even
yeah, that would be difficult to orchestrate if it's completely controlled. I mean, the best thing I could think of is just doing small changes that you think could, like say there was a hurricane, maybe there's something you could do to just nudge it this way and then have it turn into a bigger catastrophe. But I don't know. I haven't seen any evidence suggesting.
I mean, I was listening to Alex Jones today talk about these beacons where they have these frequencies. They don't say what frequency it is or what wattage or amplitude it's transmitting at. None of the physics stuff that we could do something with unfortunately. But he's claiming that the frequencies can actually control and move the storms and stuff, and these things sound fantastic. They sound plausible, and right before an election, it's no doubt that people are blaming the government for hurricanes and weather and everything they can. But at the end of the day, we rely on mathematics and scientists to be able to sort this stuff out for us and figure this out. Is this legit, or is this nonsense? And when you start getting into the real physics, like orders of magnitude, right?
Yeah,
orders of magnitude is
powers of 10,
right? It's just the powers of 10, right?
You can do quick back of the envelope calculations. That's what physicists' bread and butter is. Just you want to quickly solve a problem, just try to figure out what's the order of magnitude of what's going on. Is it even in the ballpark? Engineers, they're going to get more into the details of the factors of 2. They really need to get it down. But sometimes if you're just evaluating if a claim makes sense, sometimes it's like, oh well, you're 10 orders of magnitude off, so that there's nothing to talk about anymore.
Right. And I think wasn't that some of your arguments against Sal Pays and his ideas for breaking the Schwinger limit, right?
Yeah. So Yeah, this is puzzling because there is this Schwinger limit, which is essentially once the quantum vacuum becomes nonlinear at the classical level. So Maxwell's equations break down above the Schwinger limit, but humanity hasn't really been able to experimentally demonstrate this. Pretty much all physicists believe it'll happen. There was talk about 4 or 5 years ago of some Chinese experiment being able to be up and running by around 2023 to confirm this effect, but I never saw anything more about it.
Yeah.
I'm not looking at everything. So yeah, I mean,
So-
it's theoretically possible. It's probably within our reach. I remember being an undergrad and thinking that, oh, this is probably like 50 to 100 years out of reach. And then, it surprisingly accelerated where, maybe it can happen in 10 years, but still, I mean, Sal Pies essentially was saying that he was playing in a laboratory with magnetic fields and talking about the Gertsenshtein effect, which relates to the Schwinger limit. And well, at least in the way he was invoking it for sure.
How do you spell it? Gertsenshtein?
Gertsenshtein. I just sent it to you in the private chat. It's Gertsenshtein, if my memory serves me correctly.
Let's check it out. A simple derivation of the Gertsenshtein effect.
Yeah, if you search like archive, you might be able to get access to the paper more easily.
All right, guys. So the Schwinger limit, right? So we bring this up. I mean, people might have heard that from the Jack Sarfati rant, where he's nothing to do with the Schwinger limit, right? The Schwinger limit was invented, come up with by this guy Julian Schwinger, who was a very intelligent.
Yeah,
he's one of the top.
People remember Feynman, but he was the one when the conference came out and QED was kind of being undercovered. People didn't take Richard Feynman seriously at first because Julian Schwinger had the rigorous details, but he kind of prided himself on being the only person able to do it. So he was this rigorous guy who was able to really figure out the nitty gritty details. But Feynman was kind of the one who brought it to the people, if you will, and made it a little bit more understandable for people to actually digest these computations in quantum field theory, which are enormously complicated and we're still trying to figure out to this day.
Right on. So hopefully I can be like Feynman and you'll be the Schwinger the next I can help explain it to people.
There we go.
Along with Bernie. So right. Anyways,
yeah. So I mean, essentially, Sal Pies, I mean, from what he was saying, it seemed like he was about 10 to the 8 or 10 to the 9, I forget which one, off in terms of the magnetic field strengths he would be required to reach that. And so I didn't really understand. It's like, okay, how are you claiming that you're using this effect in your laboratory? And at the end of the day, I don't really like being too negative to people. I just try to understand things and ask critical questions. I'm not trying to bash people, but there's certainly exotic phenomena that I'm not aware of. So maybe, I've heard claims that there's this idea that somehow graphene can somehow bring the Schwinger limit down. I don't like, it was some I think it was a theoretical paper. I skimmed through it. I'm trying to remember the details. I mean, I don't know. I'd say more research needed. I don't know. I still don't really
science
understand.
Might be the way to do it. Sal Pays was using the lead zirconium titanate, the PZT, and whatnot. But the whole idea is that you take these wave fluctuations, so you're actually you don't have to pump all of it in at once. You can kind of like catch it on a good pulse. And then the idea of breaking those up into super pulses and stuff too seem to do something. And then the idea of well, how much energy is this first off, and how
basically the world's most powerful laser is like not quite there yet.
Yeah. And then the way I put it too is if you could take a kilogram of matter and convert it directly to energy and then squish that down into a nanometer. That's how much energy this is.
Yeah, it's a crazy amount, but it was strange though, because after Sal Payas had that talk, I was watching some video from Eric Dollard, talking about Tesla stuff, and there was something he was saying about longitudinal modes that it sounded like he was getting something where, yeah, okay, now I remember Sal Payas, I was like, I think you're kind of off by 10 to the 8. So, and then there was something that Eric Dollard was talking about that sounded vaguely similar to vacuum interactions in the Swinger limit. It was like a bit of a stretch, but it was like 10 to the 9 lower than what I was, anticipating from our current understanding. So then it was like, okay, well, if these things happen to be related, then maybe there's something that I just don't understand yet that could lead to it. But I don't know yet. More research is needed, really. It's kind of speculative. It's a very loose connection at best. So it's important to stay open-minded and be critical. And I try to oscillate between the two. So one day I'll be very optimistic, hope for the best, explore some crazy idea and assume, hey, maybe everything will work out. And then the next day, or maybe the next week, I'll try to rip it to shreds, try to prove it wrong. And so it's important to do both those things, or you could just be level-headed throughout. But I think you can be a little bit more efficient that way, or even just like kind of guess the solution and then try to prove it right or wrong later. So yeah, it's definitely you do need to stay open-minded, and it's important to stay grounded in what the mainstream is saying and try to see what's coming next. I mean, that's at least my perspective. I try to stay grounded on both sides, and I'm trying to bridge the gap between conventional academia, but then also these more fringe ideas. But it makes it very difficult to communicate because I have to be careful about the way I word things, because if I say something to one audience, it's going to deter the other audience. So basically, I'm probably not communicating well to anyone, as it turns out. But I think it's important to try to bridge that gap. Otherwise, it's just you're gonna get this continual echo chamber of people on the internet just parroting what other people are saying, and then it just leads to more division. And then the people in academia aren't gonna take these ideas more seriously. So there needs to be some way to kind of bridge the gap, especially if there is something here. If we do believe that there are UFOs out there and they are using exotic technology, there has to be some scientific explanation for how it works. And currently, and so we're at this curious point where scientists are more open-minded than ever to consider the possibility that UFOs are real, but it's too difficult for them to really understand how to get into it, to actually research it regularly. I'd say at this point, it's not that they're trying to suppress the topic. It's just really, it's a new thing to them. They don't have the expertise, and they're trying to focus on the things that they feel that they have expertise on. So everyone wants to put their best step forward and present themselves in the best light. So it can be difficult going into completely uncharted territory.
Yes. And a lot of this math, it just looks like scribbles to people that haven't, familiarized themselves with, delta operators and partial differentials and the other things that I see.
That's actually a nabla. Yeah.
Oh, that's a nabla operator. It's upside down delta. Yeah,
exactly.
Delta.
See, right? It's like a completely different language, not even Greek. You don't even know where these symbols come from.
Right. And then what this phi of R and T, I mean, what's that? That's the wave equation, obviously. I know that from this EXP, that's an exponent to,
And the other thing, to really get to a more advanced level, it's like the symbols aren't the things either, right? So when you get into the weeds, different papers might use different symbols for the same thing. And as a physicist, you need to, it's easy to just say, oh, psi is the wave function, right? But no, that's just a notation for the wave function. And we have the freedom to create whatever notation we like. But at the same time, it is extremely helpful to develop a common language. So, I do try to stick to standard notation whenever possible, just because communication is extremely difficult. So that's another thing. Sometimes when people go off the beaten track, they might have good results, but if they're not staying in contact with how most people communicate things, it makes it more difficult for other people to understand their work, which then leads to delays
But then also, like, the more precise you are with your language and stuff, the less that normal people can understand you because they don't, they don't get the context either. So it gets into some rocky ground here with science communicators like myself that try to take these topics and bring people from both sides together on them. One of the most craziest things is this whole when you start talking about gauge theory,
Mm,
and
I love that stuff.
so I know that you love that stuff, but I mean that some of it makes our heads hurt.
I
I
will say with all of that, I remember definitely very clearly feeling like I didn't understand gauge symmetry. I didn't understand Lie groups. And I remember just getting to a point in my education where I felt like I understood some basics. I could do some math problems with it, but I always felt like there was some deep, mysterious thing about it that I didn't understand. And eventually I just reached this day where I said, I think for the most part, like there's not much more. Like even I've seen a lot of physicists get confused about it too, and they almost get scared of it. They understand the basics, but they feel like there's something deeper. And there is. I mean, there's some geometric details that often are a little bit more advanced. You can get into fiber bundles and stuff like that. But
Yeah,
at the end of the day, group theory it's not too difficult. But for whatever reason, it kind of gets put up on a pedestal. And I mean, really, at the end of the day, it's about continuous symmetries. So the quintessential example is just rotation groups. So if you have a circle, I can rotate a circle an infinitesimal amount, and it's still a circle. And so you have this object, you apply a transformation to the object, and you get a transformed object coming out of it. And it's very much like a function, right? Like y is a function of x. X is the input, y is the output. It's kind of the same idea. And so now you have this geometrical object like a circle, and you can rotate that circle from by any degree from 0 to 2 pi, and it's still going to be a circle. And so there's the symmetry group associated with those transformations because it leaves the circle invariant. You put a circle in, you get a circle out. And really, it's just that concept generalized to more complicated objects. So then you can study spheres, and then you can go into
right. And
spheres in higher
this is a
dimensions.
way like that. If you're blind and you don't have the whole picture of the object, you're just on a piece of it. You can move around a little bit. You can use math to be like, oh, well, this is circular, like, or
Right.
to kind of draw these associations to different objects, and it goes deep
Yeah, it's rich. It's rich. It does get deep. So like you have an angle that you could rotate something on, and now you have a sphere. Let's say you have a sphere embedded in it's a two-dimensional surface, but it can be embedded in 3 dimensions. And so you're going to have multiple angles that you can rotate between. And the parameters, those angles, actually create a geometrical space because you could rotate this way by say pi, but then you could rotate another way by pi over 2, right? Or you could rotate by any value that's in the domain specified, and that gives you this geometrical space that's a little bit more abstract. And so that starts to get into some of the deeper stuff there.
the
Yeah,
quotient. Yeah,
quotient
you're talking about
spaces.
quotient spaces and vector spaces and Hilbert spaces and
Oh yeah,
non-Euclidean spaces, and then de Sitter anti-de Sitter space.
yeah,
What is all
yeah.
this? What are all these spaces and how?
Well, yeah. Let's take it a step at a time. I mean, yeah. Let's save Hilbert space for a little bit later. We can get to it if we want, but yeah. I mean, a quotient space. I mean, oftentimes the ones that I've seen end up being basically like a Lie group, which is one of these continuous symmetry groups divided by another Lie group. And so you can actually formulate space-time as a quotient space. And so, or even space. So if you had a sphere in, let's say, d dimensions, and then you had a sphere in d minus 1 dimensions, you could take the quotient space of those two and actually get a vector space out. Let's see. I'm trying to think. let's try to break it down even simpler. I mean, okay, so you have a sphere. You could have the points on a sphere, and you can imagine all the ways you could rotate that sphere. And then you could pick a circle on the sphere, and you could have the rotations on that circle. And so you can then imagine that you have the symmetries of the sphere, and then you have the parameters, those angles that form a coordinate space, and then you have the angle on the circle. And if you remove that angle, you're going to have one angle left. And so that angle that's left basically forms a quotient space, and it's just it's just like a vector space that you get left over. And so you can actually form space-time that way by just kind of generalizing the concept of spheres and then adding some non-compact stuff for time. I do need to get better at simplifying it even more, but that's almost as simple. I could probably make it a little simpler somehow if I really tried, but that's almost as simple as I can make it. I mean, that's this probably the simplest example is just thinking of a circle on a sphere, and then realizing you could rotate on that. You're on the sphere. You could rotate on the circle, or you could rotate away from the circle, and basically all of the rotations that are not on that circle form this quotient space, which can give you a vector space. So that's one way to think about it.
And this is, these are important because, if you want to take fields, for example, like electromagnetism, and play with it, you need vectors for one. Vector calculus is essential for understanding Maxwell's equations. I mean, Maxwell's equations and a lot of physics is actually based on.
That's how it currently gets taught in undergrad. It's, you don't need it, but it's definitely a good way to look at it because the language is so developed and humanity has invested so much in this notation and this formulation. And so we have this idea that the electric field is a 3 vector that points in some direction. And you also have the magnetic field. So if I take a coil, I have a solenoid, and if I put a current through that coil inside the solenoid, there's going to be a magnetic field that's roughly constant and pointing in some direction. And the direction that magnetic field is pointing in, that is a vector. A vector is just a mathematical quantity that has a magnitude and a direction. And then there's different operations. You can take the dot product, which is like an inner product, which you could have 2 different vectors and see, like, if I have the shadow of one vector on the other vector, like how big of a shadow does one vector cast onto another vector, and that information is encoded in the dot product. And then there's also this cross product, which kind of is almost dual. It's a little bit opposite. It's kind of like, so the dot product tells you like how parallel things are, and the cross product tells you how perpendicular things are. So you could have 2 vectors that are perfectly 90 degrees perpendicular, and that's when their cross product would be the highest. And then from there, you can introduce differential operators, and you can have calculus. So then you can take a derivative, and then you get this gradient operator, which has that nabla symbol. So you can have like ddx, ddy, ddz. It's multivariate calculus. So, it's what, calculus 2 or 3, depending what university, whatnot. So
the derivatives
it's a little
are
sophisticated.
interesting.
I mean, a smart high schooler can get to some of this a little bit at the end of the high school if they want, but most people would learn this in undergrad. And
there's some advanced placement. I remember some couple kids were in like calculus and taking like that in high school and stuff, but I really didn't dive into this until college. Get into it and have to really, and then a lot of kids dropped out because it was just too much math for a lot of people. They're some people.
It takes some time. Yeah. It can be a little difficult, but it's doable.
I thought it all wasn't that bad, and the physics actually helped me to learn and understand the math better. Because I was not just a pure numbers kind of guy. I had to like do like some problems in physics, and then and then to realize, oh, you need calculus for this. I was trying to figure out, oh, you have this equation, then how do you figure out the velocity if this is the acceleration? And I was like, oh, I didn't know how to take x squared and just make 2x.
Yeah.
I didn't know that, like, that rule with
Oh, you just take the exponent and bring it down and then subtract one exponent. Yeah, and then it turns to this thing where you kind of just remember all these facts or all of these rules and you don't think about it for a while, or you could try to have a deeper understanding. So it's good to do both. It's good to understand things from multiple angles. Sometimes it's quicker to look at things one way, but then nice to understand the rigorous details. So if you need to, in some case, you could work through and derive things more carefully.
Yes, and so this stuff, would you recommend set theory and group theory, like, for an undergrad?
Yeah, potentially. I mean, if they're interested in doing it, yeah, certainly. I mean, if they're into math or physics,
Because the
yeah,
set theory stuff was like, yeah, I didn't take set theory and group theory.
I never took it either. I never formally took group theory. I mean, I went to MIT for undergrad, so it was this kind of thing where a lot of physics curriculums, they have this mathematical methods class. We didn't have that in our school, so they would just kind of teach that, like, we just kind of had to learn it in the physics classes itself. But if you were going in theory, it was always suggested to take math classes as well. But I personally decided not to do that.
Yeah, I
I
had
took some.
Boas. That was the textbook I had. I had that same class. It was called Math Physics, and this was our textbook.
Yeah. See. Okay. Yeah. I once I got to UCLA, I had a graduate class that had a mathematical methods class, but I didn't have it in undergrad. So I ended up basically just picking up group theory on my own through the years of just studying it and Lie algebras and things like that. Honestly, a lot of it, and it's strange. I don't even know exactly how I learned all of it because I don't even have good textbooks to recommend to people. I didn't learn it from textbooks. I just kind of was studying.
This is a good book that was recommended to me. Lead Groups for Pedestrians.
Yeah. Yeah, I'm not familiar with that book. There's a few classic books that a lot of people refer to, but honestly, it got to a point where some of the research I was doing, I would skim through the books and it didn't have the information I wanted because I was getting into these exceptional Lie groups is kind of what I got obsessed with. And so that's kind of a special topic within itself. And there's very little information. So honestly, what ended up happening is I collaborated with an expert named Alessio Morani who really knew his group theory. And I would just grill him with questions for like 2 years straight to learn about all these details.
That's how
being able to be in contact with experts so you can just ask them your specific question. I mean, honestly, with ChatGPT as well and AI and all these LLMs, that makes it a lot more accessible as well.
That's if they don't lie to you, if they're giving you legit answers.
Yeah, that is true. The concern is it's difficult to blindly trust AI. I wouldn't recommend that, but it's getting better and better at if you kind of can start to understand like what might be more popular or more commonly discussed. I mean, I would be at a point where if I were to ask ChatGPT what is the definition of a group, I would be, I don't know, I'd say I'm 95 to 99% confident that it's going to give a good answer on that. Right. If you're going to ask it some details about, give me an elementary example of what a Lie group is and what are all the elements in a Lie group, what's the generator of a Lie algebra, what's the definition of Lie algebra, I think it would do a great job of answering all those things. I asked a question. I said, can you classify all of the maximal compact subalgebras of this non-compact real form of E8? Right? Like that sounds like a more advanced question, right? And to my surprise, the new models, they did pretty good. It didn't get everything right. Claude actually did a little bit better than ChatGPT there, but it was like neck and neck. They gave like a half full classification and maybe one. I think ChatGPT made like one error, but other than that, it was like pretty decent, surprisingly decent. And that's a very technical, advanced question. So I would say if you're trying to learn, if you're an undergrad who doesn't have the time to take these math classes, you can certainly, I would say at this point, rely on AI to some degree to learn the basics, and then try to just quickly, learn it that way, and then go on the internet and see if you can verify what you learned there. That's another strategy that I'm employing now for research. It's like we can't just blindly trust AI, but it's kind of a shortcut, right? It's good for brainstorming. It's good for starting the process. So you can just get this customized response for what you're looking for, and then you'll learn something and just think of it as a claim. And really, everything you learn, you should think of it that way. I mean, it's a little convenient to just blindly trust the professor, but I remember doing that as well, where I went to a prestigious undergrad, so I just blindly was like, okay, I'm learning this, that they're the experts, they must know, it must mean that for these undergrad classes, everything they
Yeah.
teach me is probably spot on. And then eventually, by the time I got to graduate school, I realized, oh, there's a couple of cracks here and there where there's even subtle solutions of Maxwell's equations that I think are taught in textbooks, or just one in particular, the Lienard-Vickert potential. In my opinion, I think it's applying the boundary conditions improperly, and is not really the best solution, but it's still taught in textbooks. Feynman talked about it. A lot of people talk about it as if it's just solidified. And so there might be little things here and there, not everyone's perfect. There's, we're all humans here, but it does help to at least trust people at first and then try to verify it later. Right. That's kind of how I approach it. And you can look at AI in the same way, right? Just see where it goes and then go from there. But, I did want to get back to your point. This is going a while back. You were saying people are talking about how there's no progress in physics, and I just want to elaborate on why I think that's just utterly not true. I mean, what is happening right now is there's just an explosion in science that's occurring. There's just more work being created than ever before. There's more published papers. There's more researchers. I mean, if you were a physicist in America in the 1800s, in the late 1800s, there's a small handful of you. You could single-handedly read all of the papers that were being published by all of the physicists. Now, imagine if you're Ed Witten and you publish this paper that becomes seminal and it gets 10,000 citations. And you introduce this novel idea. How are you supposed to remain an expert in that domain if you get 10,000 citations? Are you supposed to read every single one of these 10,000 papers? Nobody has the time to do that. And so, yeah, I mean, there's a lot of bad papers too out there. Like anything, there's good products, there's bad products, right? Have you ever bought something where you're like, oh, that wasn't what it was sold to be, right? That happens all the time. So it's very easy to just look at this huge body of literature and cherry pick a few papers and say, oh, well, I looked at 5 papers this morning and I don't agree with any of them, so science is going in a bad direction. And it's like, well, in my opinion, that's not the right way to look at it. It is a skill as well to understand how to tease out, how to quickly read papers, how to skim them. And that's something that takes time. I think every expert physicist eventually finds their own way to do this. And so when I hear someone like Sabine going out there, or Eric Weinstein going out there saying that physics is dying, I mean, let's make it more specific. First of all, condensed matter physics is crushing it right now. That is the leader in physics. High energy particle physics is dying. And the reason is because we're running out of experiments to do because we don't have enough money. And so what else can theorists do if we don't have experiments to do? And I'm not trying to blame the experimentalist either, right? Like, it's just we have a finite amount of resources that we have access to, and you have a time window where when you're starting science, you have these resources, you can use them to your advantage and you can learn from that. But eventually, once you've explored every atom on planet Earth, once you've explored every possible way you can collide particles and get higher and higher energies, and once you start putting billions of dollars into these colliders, it gets to a point where there's not that much more that you can do with those types of experiments. And so it puts us in this troubling spot, because now it does lead to more speculation. It does lead to, you could talk about string theory. Oh, how this promise, people have been discussing it for 40 years and there haven't been any experimental results. But you have to also understand that string theory primarily is about a high energy theory of everything that's touted to be a theory of everything that's really appropriate above the Planck scale, which is this exceedingly high energy range that we can't even come close to reaching. So really what's happening is everyone who's in this field understands that string theory is not really meant to describe everyday physics, but they wanted to try to convince politicians, let's say, that there was a chance that it was working, and some people believed there was a chance it would lead to detection of superparticles at the LHC. And yeah, there was probably some errors there, errors in judgment. And there were students who trusted their advisors and said, hey, well, my teacher is telling me that the LHC might detect, this is like 1970s, 1980s, 1990s. There's tons of young people getting told, well, there's a good chance the LHC or, whatever particle collider of that day, the colliders might eventually find these particles. But if you actually critically study those things, I mean, there was a chance, but there wasn't really. You could say it came in at any energy scale. You could put it wherever you wanted, and they can always push it up. So it doesn't mean that the theory is unfalsifiable necessarily, but there's a lot more wiggle room in string theory than they like to make it seem. It's really a lot more vast and complex than they like to make it seem, because they're trying to simplify it and they're trying to dumb it down, and they're trying to tell the story of, hey, we have this one theory called string theory because Ed Witten unified all the string theories, whatnot. But it's more complicated than that as well. So, I kind of have a balanced, nuanced position on this. I mean, yes, to some degree, particle physics is decreasing, but that doesn't mean all of physics isn't flourishing. Condensed matter is killing it, and let's be honest, it's probably more useful for humanity to study condensed matter. That's trying to understand how do we explore more exotic materials, right? If we're going to want to understand metamaterials, we're going to want some condensed matter physicists on this problem. And then some people, I've heard people say, oh, well, that's not fundamental physics. We're just trying to understand this. Or I'll talk about some advancement in quantum gravity, perturbative quantum gravity, that you have the graviton, which is basically gravitational waves, just as the photon relates to electromagnetic waves. You can look at it that way. It's completely fine. And so for the longest time, really, this whole problem with quantum gravity was because when they tried to do graviton scattering, they got infinity results. And so it was claimed to be miraculously finite at the first quantum correction. And then you got this UV divergence. What that means is a high energy divergence where you got these integrals, and you do the integrals and you got infinity when you're trying to get a probability in between 0 and 1. So you get this nonsense answer. And basically what ends up happening is it took 40 years to make progress on that problem. And Zvi Byrne and collaborators found a solution about it in 2017 or so. And nobody's talking about it because he wrote it so cautiously. And then you get people saying, oh, there's no progress whatsoever. But I mean, there's just so many papers out there, it's hard to find the progress.
Right. Yeah.
So that's my rant on that.
Yes. No, that's not my wheelhouse at all. That's your wheelhouse, man. Thank you for that. It's super, that is super interesting. I wanted a couple questions from the chat and some questions that I had. I don't know if you saw that interview that was done by Jesse Michaels with Hal Puthoff and Eric Davis.
I haven't yet. I would love to watch it at some point. I've been very busy.
This is, I think it was 2 years ago. This was posted. It's about an hour long.
Okay.
And they had this discussion. I mean, one of the highlights from it that I wanted to ask you, I think it's this most replayed part, is where, Hal suggests that a lot of physics has been classified, and that we might not have the full picture because string theory wasn't classified, and that's what was pushed predominantly. In some ways, some physicists believe that string theory was allowed because the classified stuff was kept hidden. What do you think about that? Do you think that would be possible to classify and hide major discoveries in physics that we might be delayed?
I think it's certainly possible for multiple reasons. I mean, first of all, just when I was at MIT, I remember my second research position. I went into this building where just to get in, you had to have your key card or whatever. And, it's obvious that the funding is coming from the military. And so what they'll do is they'll kind of, obviously there's some big application that they want to use technology for. That application doesn't really get told to the scientists. So what they'll do is, I don't know, there must be some committee or something that's trying to break it down and to say, oh, we need to understand these 5 ingredients. Like if we really understood the fundamental principles, like a good example is cloaking technology. I think that's a perfect tangible example. Like there's enough information out there where, it's not completely dark, but it's likely that there's cloaking technology that exists that all the details aren't public. Right. And so, the basic idea is you want to make a material so that certain frequency of light will kind of bend around it rather than reflecting off of it. And then that way you would never see it, because in order to see something, you send light, bounce it off, and then you get the light back and you detect that. And so you definitely have these scenarios where government organizations in the military are essentially funding scientists to work on these select problems. And obviously the military compartmentalizes this things. And so that kind of paradigm gets brought in. And so you'll get these different groups working to solve very specific problems, right? And then obviously when maybe that result gets published, right? But the implication of that result might not be immediately obvious to anyone. But I bet a lot, what happens a lot of the times is that what gets classified is more like how to connect the dots. I mean, obviously there could be fundamental theories that could get classified too. I don't know. Like, I can't think of like good example.
Yeah,
I don't know.
hard. It'd be hard to like, something that fundamental, that because it would just get published in the journal, and then you'd have to worry that, the Russians or the Chinese or something would discover it too and then just publish it. But like a lot of times what gets classified is the technical details on the experimental setup. So they have the paper with the results, but if you were go to like ask the scientists, well, what kind of this did you use to build your setup, and that kind of information is the technical details that are protected a lot of times. But yeah, I just was curious on your opinion about actually like derailing physics and classifying certain things and from us altogether. And I saw what happened with cold fusion too during the 1980s, that was taboo for pretty much all the 90s to even talk about it or mention it, and then only during like the 2000s did it start to get reborn again, and now it's sort of safe to talk about if you call it an LENR, low energy nuclear reaction, and don't call it cold fusion, right? So it's kind of like,
yeah, the Cold War definitely did have a big impact on a lot of this, because there was just so much heightened tension on keeping information secret and always getting ahead. And, I mean, this has nothing to do with science. It's kind of this thing where, well, if they're dealing drugs to make money, we need to do it too, or this and that. I think really kind of what happened is during World War II, you're trying to get information at the docks, and the mafia is like running the docks. So then that's where corruption starts to get in, and then there's more blackmail, and then it, it kind of corrupts morals a little bit. And then you're in this, competitive environment where you want to stay ahead no matter what. And so it does make sense from, a national security standpoint. At that point, there could be certain things, or I mean, even the case of Nikola Tesla. I mean, I suspect it's likely that he was put up in that hotel, and I don't know if the government paid for it or something, but I mean, what happened was he was talking about that death ray, and he was trying to get funding for his science, and it got to the point where no one in the US wanted to fund him, because I see both sides of it. Once again, I love Nikola Tesla. I wish he, there was more of his understanding of his worldview was like more accepted, but at the same time, and I could just bash JP Morgan all day, but like at the same time, you have to understand, like realistically, it's like if an investor gives you money for a business, you can't just take that money and completely lie on how you're going to use those funds. I mean, that's just not like, it should make sense to most people that that's not a smart thing to do. And that's essentially what Tesla did. I mean, he tried to create free energy for everyone when he told his investors that he was going to make it for them. So that sent a shockwave into the US investment, where they're like, well, why would I fund Tesla and put if you're trying to put money in things to get money back, why would you fund something if he's just going to take it and then give it away for free? it would help humanity. That's totally great. But I mean, a donation is different than an investment. So you just have to be honest about that stuff. So it got to the point where Nikola Tesla is talking about these death rays, and he started talking to internationals. And I forget if it was, I think it was Russians at some point. And I think at some point, the government kind of came and was like, look, okay, maybe stay in this hotel for the rest of your life, but don't take, foreign investments, because we don't want you sending death rays around, right around World War II time period to foreign countries. Obviously that's a thing of national security. So it's a delicate subject, it's complex.
Yeah, it gets into some weird, like another guy like Nikola Tesla that I wanted to talk to you and ask you about is this gentleman right here.
Yes.
He gets brought up in a lot of the free energy
Oh yeah.
people saying that they have free energy. They'll bring up Tom Bearden and his work and stuff. Another big thing I wanted to talk about is something he mentions a lot is the scalar physics and scalar waves.
Mm-hmm.
So I know you've done a ton of research into the Tom Bearden stuff, all the electrodynamic stuff that he was talking about, and really I don't know how much of that you are willing to share or you can share of that.
I'll talk a lot more about it than I usually would. So I've been very careful about this topic. Essentially, I'll just kind of tell my personal story about how I got into this. So I was studying quantum field theory as an undergrad, and I just thought about the idea that science typically leads to engineering in ways that we can't imagine. And I was just utterly fascinated by the existence of the quantum vacuum. And so I just put faith in this idea that there has to be some engineering applications of the quantum vacuum. And so I started, even though scientists are saying it's not possible. So obviously, if you start searching around on the internet, especially in a decade ago, you're going to run into Tom Bearden. And so it's this polarizing topic in the sense that he certainly has a lot of passion towards this topic. From the lay point of view, I mean, he seems like he's making a lot of connections that seem very legit. And so as I started looking into more of the details, I found the situation to be extremely complex and subtle, where basically a lot of times some of the things you're saying are like technically wrong, but he's sort of close to something. Like he'll talk about quaternions, he'll talk about the history. And so, I'll admit that Tom Bearden inspired me to read Maxwell's treatise. And so I remember in graduate school, one of my professors told me to not read Maxwell's treatise. They're like, oh, it's a waste of time. It's too difficult. It's antiquated notation, this and that. And so I remember at that time that just like motivated me to look at it even more. Right. And so he's making these claims, and there's some partial truths, but then there's also false things. And so that's what makes it even more of a complex scenario, because if you're an academic quickly looking into this, it's very easy to just find 2 or 3 things that are technically incorrect and then just dismiss the whole thing. So essentially what I've been trying to do is, I'm probably not the world expert on Tom Bearden. I haven't read everything he's done. I haven't extensively dove into what he's saying. What I'm trying to do is look in his work to a certain degree and try to get a feel for it, and then go back to the history and go back to the literature, go back to some of the greatest scientists and see what they said, and see what we can do with things like quantum electrodynamics and things like revisiting Einstein's unification and seeing how can we take those ideas and see if it confirm or denies what Tom Bearden is saying. So, for instance, he'll talk about the quaternions. And it is true that Maxwell used the quaternions at some point in his treatise. But it's not true that the quaternions lead to new physics. It's not that because he used quaternions, that Maxwell used quaternions, he was getting more physics. That's a false statement, because you can use 3 vectors as well and get the exact same equations. But it is also true that Hertz and Heaviside to some degree reformulated Maxwell's work. So it's like one of those things where it's like kind of correct, kind of wrong. He'll also talk about this, how Heaviside basically made a correction to pointing, right? This non-diverge and diverge. So there's this notion of a near field, which is basically electromagnetic radiation very close to a source. So if you have like an antenna and you send some charge down it, it's going to radiate some electromagnetic energy. And so you can go in the near zone, very close to the antenna, or you can go to the far zone, really far away. And it took time for physicists to understand that the solutions in the near zone were different than the solutions in the far zone. And that was what Heaviside was pointing out. And so there's some partial truth to what Bearden is pointing out there. And then it gets in these things like scalar waves, longitudinal waves. And this one, it is also like some partial truth to the idea that people say, oh, longitudinal modes don't exist. Like, you might hear even professors sometimes say that, but it's technically not true. The true statement is, at least with our current understanding in the mainstream academia, is that longitudinal modes never make it to the far zone. But a less talked about point that is true, and is, if you're an expert in this stuff, you should be able to understand this, that in the near zone, you can have a component of the electric field that has a shadow on the direction of propagation. So that can have a component that is longitudinal. And so there are waves that can exist in the near zone that are longitudinal. I mean, it's also found in waveguides. That's very well understood that you can have longitudinal modes in waveguides. They'll have TE or TM. And so that's fine. They'll call it transverse electric, right? In the name, they're talking about what's transverse, and they're leaving out what's longitudinal. When it's transverse electric, that means it's longitudinal and magnetic. So it's almost like they're trying to word things in the way so it sounds as least controversial as possible. So you have to do a little more digging to really see, oh, a TM wave is transverse magnetic, but it's actually going to have a longitudinal electric component once you dive into the details. And then there's also certain plasmas can have longitudinal electromagnetic waves. And then, so yeah, historically, there was this debate on whether there were longitudinal modes. Back in the day, Tesla believed that basically everything was a longitudinal mode, and he was kind of denying these transverse modes. And so I would say I think it's a little more subtle, and there's kind of both going on. And then, so then it got to this point where Bearden was talking about scalar wave interferometry. I found that interesting because he talked about Whittaker potentials. And so that's another obscure topic. E.T. Whittaker was a renowned mathematician, and he also wrote a few physics papers. And so he had these Whittaker potentials that came out in 1904, and they're like pre-potentials. So there's the electric and the magnetic fields, and they're force fields. And we know that force, F equals ma, so force is proportional to acceleration. And so these force fields can lead to accelerating charges. And then there's also this electromagnetic potential. And Maxwell at some points called this the magnetic momentum, the magnetic three potential, the three vector potential. And there's also the scalar potential, and those get unified into a four vector, which they'll call a mu sometimes. And that's kind of where we're at now. So Hertz essentially believed that the electric and the magnetic fields are what's real. That's what's physical. And then once quantum theory came around, the Aharonov-Bohm effect established that the electromagnetic potentials, those A's, yes. Yeah, you got some Hertz vectors, Hertz potentials, exactly. So the Whittaker potentials contain the same information as the Hertz potentials. And so the way I think about it, okay, if the electromagnetic potentials are like electric momentum in some sense, they enter covariant derivatives, which are kind of associated with momentum, covariant momentum. And then, we have P equals mv, so it's kind of like a velocity. Acceleration is a time derivative of velocity, and velocity is a time derivative of position. And so intuitively, the way I've been looking at this is that if there is some ether, then there should be something that's more referring to the positions of things rather than the velocities or the accelerations, if you can catch my drift. And essentially, this is an example of where I was inspired by Tom Bearden. I had never heard of Whittaker potentials. I learned about this concept from Tom Bearden. Rather than reading what Tom Bearden and his collaborators said about it, I went back and I studied these works from 1904, and I just started collecting trying to find as many papers as I could that would cite those papers, and studying them in detail to try to understand the more rigorous details. And so what's fascinating about the Hertz and the Whittaker potentials is that their solutions are determined by the positions of the charges alone. And so if you're trying to uncover this picture of some electromagnetic medium, I kind of like that concept that its solutions depend on only the positions. It's as if, it doesn't matter what its velocity is, right? Like, it's like, can I move a block from A to B? In order to move that block, I need to be at the location of A, at the position of A, so I can pick it up, right? It doesn't really matter what speed I'm at. I could be going at a million miles an hour. I could have enough momentum to push that block, but if I don't get right next to that block, I can't push it, right? And so that's why I think that there's aspects of classical electrodynamics that still are not well understood. And this is a controversial claim because most academics would claim that, oh no, we pretty much understand classical electrodynamics at this point. And so I would respectfully disagree. And so this is where Bearden really has inspired me. Now, but then he gets into what he calls O3 electrodynamics. I mean, his collaborators worked on that. I personally don't find much of merit to that approach. I mean, I don't claim to be an expert in that theory, but I definitely looked at those papers and it didn't really exactly make sense to me. That's not to say it's wrong, but what I did notice is that there was this Einstein-Cartan theory. And then they tried to, it was basically one person was obsessed with the O3 electrodynamics. I should say Einstein-Cartan-Evans theory. It's a very important distinction. So Einstein-Cartan theory, in my opinion, is extremely legitimate and should be studied. But what happened is there was this Einstein-Cartan-Evans theory. And, it's about trying to come up with a theory that's going to support perpetual mobiles or free energy devices, essentially. And so a lot of people are going to just try to find a way to disregard this. And when I looked into the mathematical details, to me, it looked like the authors were applying a lot of wishful thinking. It was kind of like, hey, like we like the same concepts. So let's just assume you're right. And let's assume you're right. And let's just put our theories together and try our hardest to make it seem like the theories agree to each other. But to me, it looked like they're kind of forcing the mathematics together. It didn't look to me like the O3 electrodynamics theory really fit into the Einstein-Cartan-Evans theory as good as what they're saying. I don't have much concrete to debunk either theory individually, but to me, that was enough evidence where it seemed like some wishful thinking. And especially just from the societal standpoint, at the end of the day, yes, I do want to uncover the truth, but if I uncover the truth and I can't communicate it to anyone and then I die, I personally don't find much value in that. A lot of scientists, and everyone has free will, everyone can pursue whatever they want for whatever reason they want. A lot of scientists like being isolated and just want to find the truth so they can understand it. And I think that's great because a lot of discoveries have been made that way. But for me personally, I want to try to communicate my results to scientific peers so the entire community can advance. That's just my goals. And so at that point, it makes sense to try to understand, well, what does the mainstream talk about? What's their language? And how much can I ground myself in the mainstream paradigm and push it towards some of these things that Bearden are saying? And how much can I validate and how much can I invalidate? And so another example of this is this concept of O3, which it's a Lie group, O3. It's a symmetry group. It's an orthogonal group, which relates to the symmetries of a sphere because you can rotate a sphere in 3 dimensions. And so, yeah, it's got 3 generators. Like you have the XY plane, you have the YZ plane, and you have the ZX plane. And you could rotate in all 3 of those planes. And you could get 3 different generators that generate these infinitesimal rotations. And then you could exponentiate those to get more macroscopic transformations. Okay, I'm going into too much technical detail, but when you study these Whittaker potentials and how they embed in the Hertz potentials, there's according to Whittaker, he wrote about 3 potentials, and he said 2 of them are physical. And that actually makes a lot of sense from the modern perspective because it's conventionally stated that the photon has 2 physical degrees of freedom, which relates to its polarization or its spin. Like you can have it spin left or spin right, or you could have like helicity +1 or like times h bar or minus h bar for its spin. And so those 2 degrees of freedom kind of get traced back to these 2 Whittaker potentials as scalar components. So it's just a single number. It's like a real number. These Whittaker potentials, there's 2 of them. And they fit into the 2 of these 3 vectors. And so that Hertz vector page he was pulling up, if you looked at the magnitude of the Hertz vector, it ends up giving one of the Whittaker potentials, more or less. And they contain the same information. And so there's this higher gauge symmetry, which what it means is you can rotate this vector, this Hertz vector, from the x direction to the z direction or to the y direction. You have this rotational symmetry where you can rotate this vector, but it leaves the object the same. Like the physics of the electromagnetic potential and the stuff that we currently measure, the stuff that we currently understand how to measure, it doesn't matter what direction the Hertz vector points in. And I don't know if this relates to the details of why they were interested in O3, but I just noticed that Tom Bearden was obsessed with O3 electrodynamics and these Whittaker potentials, which has this higher gauge symmetry. So it seems very likely that Tom Bearden didn't really grasp the higher gauge symmetry associated with these Hertz potentials, which is even more complicated than the typical U1 gauge symmetry. It's still a U1 symmetry, but I don't know. I don't want to get too technical about it, but basically these Hertz potentials have a higher gauge symmetry. And it actually relates to the Lorentz group or space-time symmetries, not just 3 dimensions. It's actually a 3+1 dimension thing. And the real reason to see that is because you can go back to the electric and the magnetic field. And what Einstein realized in 1905 is that you can apply Lorentz transformations. Well, other people might have sort of saw this before Einstein as well. You know, relativity, it's a progression of multiple scientists, but certainly Einstein talked about this in 1905, where you can have, sorry, got a little distracted there. Okay, so in 1905, Einstein realized that the electric field and the magnetic field fit into this matrix, this 4x4 matrix that had zeros on the diagonal, and it was anti-symmetric. So he had 6 components, and it's called the electromagnetic field strength. So the electromagnetic field strength, it's like a container that contains the electric field and the magnetic field as a single object. And so it's tempting to study Maxwell's equations with the 3-vector formulation and think, oh, there's this electric field as one thing and this magnetic field as another thing. But it turns out you can, when you're in one frame of reference, like if you're on a train versus you're outside the train and you're watching the train move by, you can have 2 different frames where you observe a phenomenon and you say, oh, that's an electric field. And someone else could be in another frame and look at it and say, no, that's a magnetic field. And they might seem like they disagree, right? They're looking at the same object and characterizing it with different things. But because there's a Lorentz transformation from one inertial reference frame to another inertial reference frame, when you study this electromagnetic field strength, you can actually transform the electric field into the magnetic field. And vice versa. You can also transform a magnetic field into an electric field. And so this provides this self-consistency where really you shouldn't think of things as an electric field and a magnetic field. It's really this electromagnetic field strength as a single object where the entire object can be transformed. And furthermore, when you apply these gauge transformations, those, like the force fields are like these acceleration type variables. You can apply transformations to the velocity, but they won't change the force fields. And furthermore, there's this deeper, higher gauge symmetry where you can apply transformations to the Hertz potentials, and it won't change the electromagnetic potentials either, and it won't change the electromagnetic field strength. And so this higher gauge symmetry of the Hertz potentials it's a little bit deep, it's a little complicated, but it's not that complicated. It's just extremely obscure. Not many physicists know about it. Not very many people study it. And in fact, the same higher gauge symmetry is studied in string theory. And so the mathematics was rediscovered, but the string theorists aren't aware of this higher gauge symmetry. So to me, I find this fascinating because to me, I'm looking at it where we might actually be able to understand, we don't have to get in this argument, oh, forget string theory. Let's just focus on maybe the military industrial complex figured out some Tesla secrets and they're hiding it from us because they stole his patent. We could speculate on that all day, but I don't want to take the risk of, I don't want to pursue a plan where I have to rely on, extracting information that are, that's secret. I'd rather pursue science and try to see what I can derive and bring into the open, or, just work in the open. So to my surprise, it turns out some of the mathematics in string theory is relating to these Hertz and Whittaker potentials, and the string theorists don't really see it. They just describe it as this gravitational phenomenon. They call it a Kalb-Ramond axion, and it's known that the axion relates to torsion. And torsion's found in Einstein-Cartan theory, for instance. And the Russians talked about torsion during the Cold War. So that led to some tension, because then the West was very quick to say, no, that's a bunch of woo, especially once the Russians were saying it was related to consciousness and time travel and unified field theory. It wouldn't be a good look during Cold War if the Russians figured out unified field theory before us. So, but that's okay. I mean, and Einstein looked at the same mathematics too, and he was very close. He was so close. He was trying to unify gravity with electromagnetism after general relativity around 1925. And he considered the metric tensor, which is symmetric. So it can have a diagonal. And so you can have a 4x4 matrix and it has 16 components. Just think of like an Excel spreadsheet where you have like A, B, C, D, and then you have 1, 2, 3, 4. Yeah, right there. You got those 16 components in a matrix. So in general relativity, you see how you have that G01? What it means to have a symmetric metric is that G01 is going to be the same as G10. So there's kind of like this reflection symmetry across the diagonal, where the diagonal is the G00, the G11, the G22, the G33. Those are the diagonal components. And the off-diagonal components are the rest. And so the metric tensor in general relativity is symmetric. And so Einstein started developing this non-symmetric metric tensor. Well, that's a mouthful right there. And so what he was doing was trying to, and I was saying how the electromagnetic field strength, which we'll call F mu nu, that was anti-symmetric. So you can imagine Einstein's excitement. He's saying, wait a second, I figured out how the electric and magnetic field fit into this F mu nu, and then I figured out general relativity, which is pretty remarkable. And now he's trying to bring it together, right? And so it seemed to make sense. Well, maybe I can combine this anti-symmetric thing with this symmetric thing to get this 4x4 matrix. And that idea didn't quite work out. He got halfway there. He was able to get half of Maxwell's equations, and he didn't get the other half. And then things started advancing with quantum mechanics, and then you had quantum spin. This is, 1925, Einstein kept going, 26, 27, 28, and then the Dirac spinor came out. This was huge. It was a new description of the electron. It brought in this new quantum field theory. We're finally understanding aspects of, the Dirac sea he was talking about. That's coming from the Dirac spinor. And so some people don't even attribute this to Einstein, but no, Einstein really was a genius, because instantly he's known as kind of being one to ridicule quantum mechanics to some degree, but he still was in the game. As soon as Dirac in 1928 discovered the Dirac spinor, Einstein immediately invented this object called the frame field. He called it the Vierbein in German, which means four-legged, because we had space-time as 4 dimensions, and there was this four-legged object. They'll call it the frame field, the tetrad, the Vierbein. It's all the same name, just different names for the same thing. And he understood that this object was needed to describe Dirac spinors in curved spacetime. And it turns out that this tetrad is like the gauge field. It's like the A mu for torsion, where torsion is like the electric and magnetic field. Mathematically, it's obviously physically different things. I'm not trying to say they're the same, but mathematically, at an abstract level, this frame field is a kind of gauge field, just like A mu, that electromagnetic potential is a gauge field. And Einstein knew to introduce this object. And so as he was developing his unified field theory, he then invented this other extremely useful tool, and he tried to reconcile that with his theory. And so then he realized that the frame field had 16 components as well. And so he actually ended up making the electromagnetism aspects worse. And so then it got to this point where Einstein's unified field theory eventually got called teleparallelism. And then it was realized that this had torsion in it. Because, and it makes sense in hindsight now that we have the history and we have all this literature that we can look back and say, oh yes, of course, his non-symmetric metric would lead to torsion. And, it's tied up with the frame field. But he ended up making the theory worse over time. And it got to a point where he ended up with this theory of teleparallelism that only had gravity. But Einstein didn't know of the Hertz potentials. As far as I don't know, maybe he did, but I don't think he understood how the Hertz potentials, there's two of them. There's two vectors. I was saying there was two scalar Whittaker potentials. You can take those two scalars and put them into a component of a 3 vector, and you could rotate the vector to point in any direction. There's this higher gauge symmetry. That doesn't matter. But these 2 3 vectors, these 2 Hertz vectors, can also get unified into this anti-symmetric 4x4 matrix. And that was published in 1931.
You have to let me find that or look it up. I don't know if I know where that is.
Yeah. Let's see if you can find it. I mean, I won't. Yeah. It took me years to find this stuff. Years, if not. Yeah. I'm trying to remember when I found that paper. Like, it took a while. So basically, with these Hertz potentials that relate to what Tom Bearden's saying, it's kind of inspired me to revisit Einstein's unification. And that's one of the things I've been working on lately. And so that's why, like, I'm trying to bridge this gap. I'm not going to just say that Tom Bearden was right about everything, but I'm also not going to discount everything he said and say, oh, it's just a bunch of hogwash. I tend to think most people in life are correct about some things and wrong about some things. In my experience, I'll hear this all the time. People will come up to me and they're like, oh, they'll send me the paper and they're like, hey, is this guy a genius or is he a crackpot? It's like, well, maybe somewhere in the middle. Is that one of the options here? Maybe he like had a nice insight but got some details wrong. That happens all the time. So I think people are too quick to try to, they want, it's like a yes or no. They want this binary output. Is it good or bad? Just tell me does it work or not? And it's like, well, a lot of times it's more complicated than that, especially if you study the history of physics. Right. Some of the most respected physicists, a lot of times what they'll do is they're trying to solve one problem. They introduce some new mathematics as a proposal for some physics. It doesn't really work out. And then turns out later that math ends up being useful for something else. Perfect example of this is the Dirac spinor. Dirac thought that his Dirac spinor would be useful for the electron and the proton. He realized that there was this electron particle and then there was this other particle that had to have positive charge, right? The electron has negative electric charge. And okay, we look around and this is 1928. So we didn't have all this zoo of particles yet. I mean, we knew about atoms to some degree. We're still trying to understand the details of how atomic physics worked. Maybe we're starting to understand more about the hydrogen atom to some degree. Okay. When was the neutron even detected? It was, what was it, like the 1930s? Don't quote me on that. But so basically Dirac had the right idea, sort of, but not quite. He thought that the proton should be used in his Dirac spinor. And then I forget who pointed out is like, no, that can't work because this, whatever this positively charged particle is, it has to have the same mass as the electron. And we know that the proton and the electron have different mass by that time. So sorry, Dirac, you were wrong there. And, time went on. I don't know who was the first to really, I don't know if Dirac immediately doubled down and said, oh, well, I believe there's something here anyways. I don't know. But time went by and eventually they realized that there was this positron, this particle that's an antiparticle. It's antimatter. That's, it's the counterpart to the electron that has a positive charge, but it has the same mass and it was discovered. So that's the perfect example of something where you're trying to solve one problem, you discover something and it turns out to be useful for something else. And this happens all the time. So that's kind of how I'm looking at this, like Tom Bearden stuff. I mean, he's claiming to be this engineer. He had these patents and stuff. It's hard to tell how much engineering he did himself. He was obviously obsessed with people like Floyd Sweet and things like that, who would have these devices that they would make. He did have this patent and then he would collaborate with all these people. It's hard to tell who did what. I've even heard at one point that there was some sketchiness in terms of who they were throwing on the author list of those papers in that, the AIAS collaboration that Bearden was a part of with the Einstein-Cartan-Evans theory, because there was this guy, Vigier, was it JP Vigier? He was the co-author in some of those. So that when I saw that name, it was like, he was this researcher who was going to move to the US to work under Einstein. And he was denied because essentially he was assumed, he was politically very left. He was like borderline communist. And so they didn't let him enter the US, and he was de Broglie, or however you pronounce it, de Broglie, let's say, kind of that, the wave-like aspects of matter in quantum mechanics. JP Figure, I might have been one of the last students under that camp. And so he was an expert in that stuff and was very solid on the relativity as well. And so he seemed to be in collaboration with them. But then I heard that basically what happened is those authors just put his name on it because they kind of knew him and they were in communication. But he didn't really endorse it. I don't know if that's true. That's just what I heard from Jack Sephardi, by the way. So
Yeah.
I don't know. So yeah, there was sometimes when you have scientists work in a particular way, you know, different communities have different ethics, different morals, right? Things you can do in the business world might seem appropriate or inappropriate in the scientific world, and things you do in the scientific world, you know, people just have different standards. So if you have this kind of fringe group that's not really hanging out with all the physicists, you know, you could have ghostwriters, right? Like it's kind of accepted in business. You know, it's like you can just write a book, pay someone and put your name on it, right? I mean, maybe some people don't think that's the most honest thing, but you know, you're not going to get like thrown out of society for doing that, right? But obviously in the scientific community, things like authorship is taken a lot more seriously. So, you know, I can also understand if someone's like coming from, let's say, outside of science and trying to, you know, be in the scientific world, he might bring in some business practices that he's familiar with and not realize that it's like not less kosher in that community, you know? So everyone has slightly different culture, and sometimes people disregard things because of that if it's not in line with their culture. But so I think it's important to keep an open mind and just, you know, stay critical about things, though. Just don't blindly accept things, but also don't immediately discount things either.
So, I agree, and you know, one of the things I use is just my back of the hand, you know, back of the hand calculations, where you know, like as a physicist, we just do some rough calculations where we're basically, you know, all your cows are spherical. On your pi is just 3, and you know, just to get a rough ballpark estimate of numbers on certain things, you can do just like we did with, you know,
Yeah,
the
here's a good one. They call it Susskind units sometimes. It's like 2 equals 1 equals pi equals I. It's like, just forget about it. You know, just don't worry about the numbers. If it's a number like 4, if it's a number like 2, you'll figure that things out later. Or another big one for physicists is minus signs. I kind of joke sometimes. This is honestly true. Like sometimes I had a research project where I believe like 90% of my time was spent just making sure I got the minus signs right. And it can be so tedious where sometimes you can do things like Feynman diagrams is a perfect example. There's different formulations of Feynman diagrams. You're reading one textbook, you're reading another textbook, you're trying to pull together insights, and someone puts an I here, someone puts an I there, and it doesn't really matter if you stay in the right convention, but you know, maybe you get off by a factor of I. That's kind of like a joke. I think even Ed Witten sort of might have made an I factor mistake in some of his scattering amplitude stuff. It's not a huge big deal. It turned out to not matter in the theory he was studying, but then people took that math and applied it to another theory, and it kind of got a little wonky. So yeah, that's definitely a common thing.
So yeah, so those type of back of the hand calculations are useful and good and easy for just rough physics, because there's a lot of claims that are taken with this Tom Bearden and the scalar wave stuff. I did a poll today on Twitter, and I asked people about the weather modification, about which technology do they think is using to, you know, how are they actually seeding the hurricanes or the storms. How are we injecting or transferring energy to the storms? Like, what is the technology for that? And the top vote of the 4 things that I offered was scalar waves. At 37% of the people voted that scalar technology and scalar waves somehow to have to do with this.
I just thought of a good point in relation to the scalar waves and Tom Bearden. So he was talking about this scalar wave interferometry, right?
Right.
And I you know, I need to go back and read what he was saying because it's been a decade or if not longer since I really dove into this stuff. But one of the things that always stuck with me is that what have we used for interferometers in terms of, you know, some of the largest experiments in human history to detect gravitational waves? LIGO.
Yeah,
Laser
LIGO.
interferometer. So we're using interferometers to detect gravitational waves. And listen again to what I was saying about this revisiting Einstein. Well, let's talk a little bit more about gravity. So you have this metric tensor, and then you have this this connection or this Levi-Civita connection, or they call it Christoffel symbols, that gets used to transport vectors around your curved spacetime, your manifold. And then there's this thing called the curvature tensor. And so one is the derivative of the other of the derivative of the other. So when I started studying electromagnetism and I started studying general relativity, without the Hertz potentials, there's only two objects. You have this electromagnetic potential, and then you have this field strength. But then on GR, you have this metric tensor, then you have this connection, and then you have this curvature. And then if you study Yang-Mills theory, if you study the standard model, you look into the other forces of nature besides gravity, you get into the strong force and the weak force. And this, you start to realize there that it generalizes the concepts in electrodynamics. They have this Yang-Mills potential, and then they have this Yang-Mills field strength. But it's also understood that if you go into kind of fiber bundle theory and you really, there's this thing called the Wu-Yang dictionary. Eric Weinstein's obsessed with this. Other researchers are as well. It goes back to the 70s for sure. There's this correspondence between the gauge potentials and gauge theories, such as electrodynamics and Yang-Mills theories, and the connection. There's a correspondence between the field strengths, the electric and the magnetic fields, and the Riemannian curvature. So I've been thinking about this for 10 years, if not longer, the idea of what's the analog of the metric in this Wu-Yang dictionary. And the Hertz potentials fit in perfectly. So
interesting.
We have the metric. And what does the metric do? It measures lengths. It gives you invariant infinitesimal lengths. It's kind of position based. And then the connection is telling you how to move on your manifold, which kind of relates more to velocity. And then you have the curvature, which is kind of like related to the gravitational force. So it's like there are these archetypes of, if you know, just like the basics of calculus, you have position, then you take a time derivative, you get velocity, you take another time derivative, you get acceleration. This archetype of like something like three layers of things that are separated by a derivative, I've been trying to understand. In my opinion, it'd be nice to have some unified field theory that kind of reconciles these things, both on the gravitational side and electromagnetism and Yang-Mills theory. And the Hertz potentials fit in perfectly for that, which contains the information of the Whittaker potentials. And as it turns out, we're currently using interferometers to detect gravitational waves. So that makes me wonder, should interferometers be used in some way to detect Hertz potentials or Whittaker potentials? I mean, it's not really a direct thing, but it seems like there could be something there with what Tom Bearden's saying from that perspective. Just from what I currently understand about unified field theory, I mean, there could be something to what he's saying there about scalar wave interferometry.
How about using the scalar interferometry to disassociate molecules and pull like metals apart, or like put the spoon inside of the aluminum block, like the Hutchison stuff, because a lot of people are claiming that the Hutchison effect is related to this this sort of scalar.
I'm still trying to figure out the details. I don't have a crisp answer to that, but I'm hopeful that I think there is something going on here. I mean, I was just talking to Charles Crawford III, and we were talking about EVOs, and he was saying he thinks the EVOs are related to the Hutchison
vacuum
effect.
Objects.
Yeah, and so it's an exotic vacuum object, right? And what I'm trying to articulate is, I think these Hertz and Whittaker potentials are telling us something about the position variables of electrodynamics, something about a deeper view about the ether, about the medium that allows for the propagation of electromagnetic waves. And so this presumably will be tied up with the quantum electrodynamic vacuum. So if there are these exotic vacuum, I still need to learn. I haven't really read that much about Ken Scholler's work. I think I've maybe just very briefly skimmed a couple of his papers before, but I've never really done a deep dive. I've never done a formal research project on the topic.
That's a good one to start with. The Rex research paper on permittivity transitions.
Very interesting.
These are like the SEM images of these EVOs, and the patterns and the frameworks that they kind of generate. It's sort of interesting. He keeps pointing out there's like these torus shapes, or the helixes, and then a torus within a torus, like a donut made up of donuts.
Right.
So these are some of the interesting shapes that come out, and then he pointed out that there's some electronics group that used this sort of thing as their symbol from like way back when. It was, he thinks it was some secret society that's protected this knowledge for forever or something. So yeah, that's Bob Greenier. His channel is Martin Fleischmann Memorial Project, and he's done some interesting experiments and research into this of his own. Again, this is one of those weird, fringe kind of things that has been it's not explained. It's
it's starting to get there. It's one of those things where there's papers out there that are related, but it's not as easy to identify how they're related. So you kind of have to really dive into the details, right? I mean, Bob Greener was talking about those toroidal moments. I started looking into those papers. We were basically getting these things that allow for, it's not radiating electric and magnetic fields, but there might be something else that is getting emitted that's electromagnetic in nature. And if you go back to the history, I mean, Lord Kelvin was trying to think about essentially like these smoke rings in the ether, which are toroidal in shape. And then, we got rid of the ether, and now it's like, oh, well, there's just this quantum vacuum that's it's just this medium, well, you can say the vacuum gets polarized. Well, if you study macroscopic electrodynamics, what can get polarized? Media, materials, objects, things. So we can have polarization and magnetization in the quantum vacuum. At that point, it's pretty much a material interpretation. And here's what's happened historically. Since quantum electrodynamics is a theory that is quantum, people kind of think that, well, any of this polarization stuff that's going on, it's just all quantum stuff. There's no like classical picture for it, because if you just look at the classical physics, that's just Maxwell's equations. In the microscopic formulation, you don't get any of this polarization. So some of the work I've been trying to do is to uncover, is there actually more you can get out of the classical theory within the framework of quantum electrodynamics? And I'm starting to find some interesting things. It's kind of coming at it, so I've been talking with Todd Desiato, who's kind of into this polarizable vacuum ideas that Hal Puthoff has talked about. And, so I'm kind of thinking of this idea. Well, the vacuum is polarizable. That's a true statement. I'm not so quick to say that, oh, this is gravity. I'm trying to just study it on the electrodynamic side. And what I'm starting to realize is that at the end of the day, to really understand what's happening, you can't just study electrodynamics. You need to study gravity as well. It doesn't mean that everything is electrodynamics. It doesn't mean everything is gravity, but if something is subtly doing something to space-time, and that subtle transformation to space-time is important for understanding the whole mechanism for how it's working, if you just study quantum electrodynamics, you're going to miss that gravitation, and maybe it'll seem like things aren't possible. And so that's where some of this more exotic differential geometry is starting to come in with torsion and non-metricity. And, I won't go into too much of the technical details here, but essentially what seems to be occurring is there's this development with these Hertz potentials that is leading to more exotic differential geometry that's beyond general relativity. And there could be kind of two sides to the story on how to look at the vacuum. And I'm kind of hopeful of this idea of, literally before this call, when I was talking to Charles about it, I was starting to think, I'm exploring these classical aspects of the quantum vacuum. I hope that this could have applications to EVOs, because exotic vacuum objects, it seems like they, are classical. It's not just like some quantum thing that you can't get any intuition about. People are seeing these orbs that they can measure, and they seem to move, and as if they have momentum and energy like classical. It's not just like popping in and out of the vacuum so fast that nobody can see it. It's like happening at the Planck frequency, right? Like there are these orbs, right? They're there. It seems like this classical object. So But if it's related to the vacuum, and if these EVOs are true, I don't know. I'm still speculating. I need to do a lot more research. So, I'm not claiming to be an expert here. Take this with a grain of salt, but maybe it could turn out that there's aspects of quantum electrodynamics that could help describe some of these EVOs. It'll probably take, honestly, I might not figure it out this year or next year, but it's definitely something I'm going to keep on my radar.
I think if you did figure it out, that could be very well be a Nobel Prize. But again, I'm not going to get into that whole politics of that. But yeah, this is interesting stuff. Yeah, Todd's a great guy. I found him through my research into Bernard Hayes and Hal Puthoff stuff. I found him mentioning a lot of that discussions and stuff that went back and all that. So I reached out to Todd, and he wrote back to me, and now he's like a big part of the whole group and stuff. And he jumped on the stream yesterday to give his skepticism on the weather weapons stuff, just based on the orders of magnitude argument on the energy of the storms and the size of everything. And I'm still open to evidence and looking at that, but I think it's going to take a lot to convince the engineers that this is what's going on. Just like with the physics of all this stuff, Ashton Forbes is convinced that this MH370 videos are of some exotic Lockheed Martin technology that was able to warp this plane and teleport it. And he was just on Candace Owens this week. We're going to have Ashton on tomorrow.
Oh, nice.
I hope that you'll join for that discussion. Ashton's agreed to have a deep dive discussion on all this free energy stuff, because he's been getting into the free energy stuff. He got into a lot of the physics when he started researching this MH370 case. Of course, found our channel and our team of scientists who are exploring the fringe on these topics and trying to navigate this whole landscape and territory, and try to break this stuff down, explain it, and prove it if it does exist in a way that makes sense to other physicists, and hopefully also help educate the community on the real physics of this stuff and the topics, which is awesome. Yeah. So there's they got the Hard Truths podcast. He's teamed up with Sal Pays and Dave Rossi. And
okay. So we can use those names together. That's funny. Okay, cool. How long have they been doing that podcast?
No, this was a podcast that was
Oh, okay. There were guests on it.
No, this was Ashton had this Ashton hosted this 7 months ago. He hosted these guys on. So this was 7 months ago that he got that. I think this is when he first got linked up with these guys. So they've been going strong kind of behind the scenes on this. I know that I was asked to be shown some things, and they told me that I had to sign an NDA, and I said, maybe I'll get someone else from the group to kind of get in on that, and not who I trust that will get back to me without telling me details and stuff and violating the NDA. So I think Mark actually signed. I don't know if Mark signed the NDA with him, but Mark signed the NDA. I know Mark signed an NDA with Charles Bueller and the NASA team with those guys. So there's some interesting stuff going on behind the scenes, but everyone wants accountability. They want credit for the work, and they want
for what work? That's what I'm trying to figure out.
I don't know what work it is yet with these guys, with Charles Bueller and those guys,
Well, that's more clear. I mean, they've been working very hard for 10 years straight.
Yeah, they got a lot of stuff, and
they're working extremely efficiently. It's remarkable. But anyways, yeah, a few things. So Sal Pays, he's been advocating for Kirsten Huang's view on a superfluid vacuum, and fairly recently I realized that yes, the Hertz potentials, those equations of motion, they precisely are the same thing as the relativistic superfluid from let's say Roget and collaborators around 1974, I believe, or 1976, right around that time. So the Kalbromond axion in string theory is known to have a relativistic superfluid interpretation, and it uses two-form electrodynamics is the name of the theory. So that superfluid vacuum theory might be a little different, but it might sort of be related a little bit.
What is I want to find something. I'm new to all what you're talking about, and you're going a million miles a minute. So I want to bring something. I'm trying to bring something up that's relevant, and I'm doing a bad job.
Let's see.
So. I'm sorry. Yeah, Dave Chester. By the way, glad you're joining us, man. You're at next level with a lot of this stuff, and a little faster than me. So
it's all good. We all have our strengths and weaknesses. I'm not by no means. I was just Googling, I don't know, this Roget relativistic superfluid Kalbromond axion.
Roget, how do you spell Roget?
Reggge. I mean, you might not find, you'll just kind of see like people are talking about superfluid vortices and things.
Superfluid reggae. No, sorry. I'm trying to find
it. Just throw in more buzzwords. Throw in relativistic superfluid, throw in Kalbromond axion, just all in one big. If you just put in too many buzzwords, eventually get rid of all the noise.
Got it. There we go. Yeah, you're not going to find any reggae songs with axions or relativistic.
Maybe that. Hey, I got the hair for it. Maybe that's my destiny at this point.
Dude,
it'll be the best reggae album ever, you know? But yeah, so, I mean, this just kind of demonstrates that there's stuff in the literature talking about relativistic superfluids. And so this interpretation has been given to aspects of strings as well, or the things that are string source, essentially, these Kalbromond axions. And I'm, just take my word for it. The equations of motion for that Kalbromond axion is identical to the Hertz potentials. And so therefore, I'm uncovering how these Hertz potentials have a superfluid interpretation. And yeah, I mean, I was looking at the work of Kersen Huang. It partially overlaps. I mean, he has, to me, he's a little vague about like what the superfluid is. He'll talk about this scalar field. He'll kind of introduce this arbitrary potential. So he's not like trying to pin everything down. He's kind of just open to this concept and trying to put some of the clues together. So it was it was encouraging to see that a lot of what he was saying overlapped with some of the stuff I was doing. But he wasn't talking about the Hertz potentials as much. So he was just talking about like, what if there is this superfluid that's kind of at the forefront into like, the foundations of how the universe works. And so I'm not claiming that this is like the theory of everything. I'm just saying that I think specifically for electrodynamics, there are these Hertz potentials that have been largely overlooked. And there seems to be this superfluidic interpretation that can be applied. And I'm trying right now, I'm trying to work out what the interpretation is, because there's this gauge freedom. There's this higher gauge symmetry. So you get this very concrete picture with the superfluid. But then since you have these higher gauge transformations, it's almost like you have three different pictures that are all supposed to lead to the same physics. And so now I'm asking the question, is it all the same physics, or is it actually, maybe there's something more subtle going on where there's actually differences that we currently don't have the right measurement devices to probe those differences. And so that's like a very, that's a bold hypothesis. So I'm basically open to the idea of what if these Hertz potentials are in some sense physical, and I'm trying to understand what the implications of that would mean. I've worked out a lot of the mathematics. I've started working out some of the very simplest solutions, but it's still far away from technology and engineering. But eventually the goal is to push it to experimental physics, where we can hopefully, maybe I'll start looking more into these interferometers. Maybe that'll help put together some clues. That would be remarkable, because
it seems like it's easy enough to build,
subtle.
It seems like it's easy enough to get like two waves, put them 180 degrees out of phase, do some destructive interference, and then get two of them interfering at different angles and see what could happen. It's definitely worth, this was a good show, man. I guess people really like the physics content. Unfortunately, I have to wrap it up like right now.
No worries.
My wife's sick. She just got out of some oral surgery, and so I got to go take care of her. But
My best wishes to her. I hope she does as good as she can.
yeah, thank you all for helping with some great questions from the audience, and thank you, David, for being here with just some amazing knowledge of just stuff that I have to go and I'm gonna have to go back. I got a whole bunch of new tabs open with new stuff. I hope everyone else does too. They've been hard at work, and I'm gonna try and get all this stuff posted in the links in the description below. And hopefully, if you can put together some links for me too, that would be extremely helpful and awesome, just so people can follow up with more reading and research on all these things that were discussed. So,
okay, great. Thanks so much for having me, Jeremy. I really appreciate it.
yeah, hopefully you can join us tomorrow for the Ashton discussion as well. So that this was super productive, and hopefully that will be as well. So,
all right, thanks everyone for tuning in, and I appreciate sharing what I can. It's good to practice trying to communicate these ideas because it is difficult.
oh, this is great, man. You did a lot of research into that Tom Bearden stuff, so that's super appreciated. And man, you really have. We got to get some questions now that people have seen this. Once this makes the rounds, hopefully we'll get some questions for you tomorrow. And thanks again for the super chats, Complazart, with the 25 pounds. That was awesome. Top one of the night, and $5 from Drake, saying he loves the physics content. We got to do more of this, definitely.
That's what it's about.
Absolutely.
We can talk about all the speculations, but at the end of the day, we just got to push forward with the science. Otherwise, that's something you can believe in. You know, if you just focus on the science, we don't have to worry about what the government's going to do, what the military is going to do. You can just make slow and steady progress and hopefully get somewhere.
Right, and then they also that keeps them off our back for spreading the conspiracy stuff, because we're actually, you know, we're on the good side, you know, the team solutions, you know, rather than just pointing out all the problems and blaming problems on everyone. We're trying to come up with real solutions to stuff. So
that's the goal.
Absolutely,
our job is to solve problems.
So yeah, and hopefully not create more ones with our solutions, right? So all right, guys, thanks everyone for tuning in. Have a great night.
Catch you later, everyone.